Okay, so the heading for this chapter is Finding the Shortest Path. I asked you to leave space for a title. The heading is Finding the Shortest Path. It's basically how do you get from A to B the quickest. So it's route planning, what Google Maps will do or sat-nav software will do for you. That's what this chapter is all about. How do we get from A to B as quickly as possible? So it's going to answer the question, how can you find the shortest path or the path of least total weight? It may not be distances between any two vertices connected by a network. Many real-world problems. Most common ones is distance, or it could be the shortest time or the shortest cost. It could be a geographical network, but it needn't be. Another application I read about was speech recognition software. Now I've got software on my phone as well that you may have it too. If you hear something on the radio, a song being played on the radio, put your phone next to it, it captures that and then looks it up in a database and tells you what the song is. That is using a variation of this. It's trying to map the song onto something else, and apparently that algorithm as well, that application also uses the same process as this. So I've so far asked you to draw this network down, and what we are going to try and do is find the shortest route from A to G. Remember, in real life, this isn't going to be as simple as this. If you did something like how could you get from here to Manchester, goodness knows how many possible roads there would be between them. The computer would know about all of them. We're doing a simple one here from A to G, and we're going to use Dijkstra's algorithm. Dijkstra's algorithm, if we put that little heading down, it's a labelling algorithm. And just looking around, what I should have said, which I didn't say, was when you draw these networks, don't draw them too small. Maybe I should have said that earlier. Sorry, Harriet. Okay, it's a labelling algorithm, and it finds the shortest path from an initial vertex to any other vertex. So you're always given a starting point, and it will then tell you the shortest way to get there. Can you two stop talking, please, as we go through? Thank you. Right, let's just go through this very quickly. The easiest thing is not to worry about this, but just go through and do it, and it will become a bit clear. But we're going to label things as we go through. Each time we go somewhere with the algorithm, we're going to label another node, and we're going to label that with what we think is the shortest distance to it. And eventually we're going to confirm those distances, and eventually we're going to get to our endpoint. So on each node, we need a set of boxes like that. So at each node, you need to draw sort of a square, split it in two horizontally, and split the top square vertically. So
that is not going to fit.
I know, if you look at this handout I've given you already, it's sort of going to be like that. You need those boxes on them. Okay? So you can squeeze them in there. You've got enough room to squeeze them in there. Okay. You probably haven't. I did say, I did apologise. You do need to draw these fairly big to get started, okay? So, you need to draw those boxes, and then, can you also at the side draw that key which tells you what goes in which box? Okay? That key that's on the board now tells you what goes in each box. Our working values will be the shortest distance that we know about to get there, but not necessarily the shortest distance to get there. The label will be the absolute guaranteed shortest distance to get somewhere, and the order of the labelling is literally 1, 2, 3, 4 just as we go along. So, if we put those boxes on, and if you make a note of that key and what goes in each box, please.